from a monitoring device had broken loose due to corrosion.
Oh, alright, so this is an F-me event. It's time for some more plainly difficult. Specifically, the doomed nuclear power station that kept on having meltdowns. Wow, glad I didn't work there. For those of you who don't know me, I'm Tyler Folst. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
This is St. Laurent Nuclear Power Station. It currently operates 2 pressurized water reactors, named B1 and B2, providing
Oh, these. Okay, I can understand why a lot of people haven't heard of these, because the consequences weren't very wide, but let's continue.
Power to the region of central France. However, today we're not looking at the setup dating back to the 80s,
Yeah.
but the site's predecessor power units, rather predictably named A1 and A2, and cited here. Today they are out of use.
So B1 and B2 are pressurized water reactors that were commissioned in the 80s, and yeah, they continue to supply safe, clean, reliable power to France. But these are more modern designs. The other 2 were gas-cooled, graphite-moderated reactors. So what France did was similar to what the UK and Japan did. They shifted from these more complex, low burnup designs, in the case of gas-cooled and graphite-moderated, to compact, high-efficiency reactors compatible with enriched uranium fuel and more standardized parts.
But each one would be the stage for 2 of France's worst nuclear reactor meltdowns.
So one thing on the term meltdown, yes, fuel damage did occur, core damage, but the term meltdown might be overstated in the sense of the way the media uses the term meltdown. So neither of these accidents, so one happened in 1969 and the other happened in 1980, neither of these involved full core damage on the scale of 3 Mile Island in 1979 or Chernobyl in 1986. They were more localized fuel melting. Significant and horrible things that you do not want to happen to your reactor core, but contained within the reactor vessel. I mean, so was 3 Mile Island, but 3 Mile Island had a lot more damage than A1 and A2. And the term meltdown, again, isn't incorrect in that fuel melting did occur, but just not on the same scale. And this is why, unless you really follow nuclear history, you probably haven't heard of these.
Rather neatly, each ranking a 4 on the INES scale.
So the INES scale, here it is straight from the International Atomic Energy Agency's website. Note that it is all highly vague. I'm not really the biggest fan of this scale, but it mainly just gives you a sense of scope rather than harm, it seems. It mainly gives you a sense of scope. So 4 means accident with local consequences. So no large-scale radiological release or loss of containment is certainly what is implied. It's kept kind of vague, but one of the biggest criticisms I have for it is Chernobyl was considered a 7, which I agree with. It was a major disaster. It had severe and widespread consequences to humans and the environment. But Fukushima was also considered a 7, which had only 1 fatality and released about 10% of the radiological material. Again, this scale is strictly a qualitative, not quantitative ranking. There are no fatality numbers or radiological numbers that go into this. But that being said, even this scale agrees that this was not on the same scope as Chernobyl, Fukushima, or even 3 Mile Island. 3 Mile Island was considered a 5, the accident with wider consequences, even though it was still localized.
You're in luck today, as we're looking at both incidents. Nuclear power in central France. Before we begin, I've just got to say that this video has been on my list for years. I actually started writing this script in 2023, but never really got around to finishing it. I don't really know why, but we are where we are.
Sure.
Our story will begin at the beginning. of the power station at St. Laurent.
Oh my.
France was rather eager to get in on the nuclear power.
These cartoons are hilarious.
Right from the 1950s, beginning with the first building work at the country's first nuclear power station in 1952, called the Mercure nuclear site. Don't worry, I won't go too much deeper into the French nuclear programme, apart from in the mid-1950s France decided to up its nuclear game, in the face of the increasing East-West tensions of the Cold War. The country, as I mentioned before,
it's like his variant of country balls.
And its first nuclear reactor type.
Kind of funny.
In 1952. The country commissioned its first nuclear reactor type, the uranium natural graphite gas, in 1956. This would be the same overall design involved in our little disasters later on. Before St. Laurent, France would build 2 power plants.
You can tell even by looking at it how relatively over-engineered it is compared to, say, the more modern hot rocks, boil water, spin a turbine that produces electricity design. I mean, ultimately it's still the same. They just got a few different moving parts by using a separate coolant and moderator.
Cool. And the Chinon nuclear power plant. The St. Laurent plant would be sited along the Loire River and was set to be home for 2 UNGG reactors. So how did this spicy machine work? Well, the design was of a gas-cooled graphite moderated reactor. It was fueled with natural uranium, constructed as fuel elements clad with an aluminium zirconium alloy.
Yes, so this design used carbon dioxide coolant, graphite moderator, metallic natural uranium fuel, so different than the 2 to 5% enriched you see today, depending on the assembly. And the aluminum zirconium alloy was chosen for both corrosion resistance and mechanical strength at moderate temperatures. And this is the same early Cold War multi-use reactor in that it was capable of both power generation and plutonium production. Kind of like Chernobyl in the sense of what it was designed to do. And France's early program, kind of like the UK's Magnox program, balanced civilian energy and weapons capability. I mean, this is just the Cold War. But the use of metallic uranium limit achievable temperatures and burn up due to fuel swelling and oxidation.
The fuel was mounted inside the graphite moderator via roughly 3,000 vertical chambers. So the way the reactor generated power was from heating up its carbon dioxide coolant via the reactor's chain reaction. The
chamber is kind of similar to fuel assemblies.
It is pumped through the core and then into a heat exchanger, where water is heated up in a separate circuit. Once heated, the water turns into steam and then turns turbines, which...
That's not too dissimilar from pressurized water reactors. It's more of just an interface with a liquid reactor coolant having a steam generator, and this one, it is a gaseous coolant operating in a closed contact heat exchanger. I guess this is just more open rather than shell in tube, it's tube in vapor.
In turn, turns generators, and bing bada boom, you've got your blackout breakfast avoiding lecky. Basically, like everything, it's all down to boiling water to turn a turbine.
Yep, nuclear and every other form of thermal generation basically amounts to this. Though a few nuances, the thermodynamic cycle for a gas-cooled reactor is going to be a little different from a water-cooled reactor in that it operates at higher outlet temperatures, usually 400 to 500 Celsius, which do improve efficiency, because after all, it's still a heat engine, which operates in an ideal Carnot cycle, so making the T-hot hotter or T-cold colder, which you can only really do in the winter when your reservoir gets colder, that increases your efficiency. And it also reduces the risk of thermal shock having a gas coolant, but it complicates materials performance, and that's your trade-off. So ultimately, hot rock's making roundy thing go roundy, but it's a bit like comparing a jet engine versus a car's piston engine. I mean, both create thrust from heat, involve combustion, but they have different...
Like nearly all reactors, they're equipped with control rods, These absorb the reaction's neutrons, reducing the power. They can also be used to shut down the reactor when needed. Gas-cooled reactors can run at much higher temperatures than other designs, allowing for better efficiency, but at a cost. Which is, well, its cost. They pose a much more money-intensive investment, which would ultimately be their downfall.
So they do require a large graphite core, because again, the gas does not act as the moderator. You need the graphite to moderate, whereas a water-cooled water is a good moderator and a good coolant. It likes heat management and neutrons, slowing them down to cause fission. But you're also going to need a bigger pressure vessel. After all, we're talking gas. Gas just takes up more space. And those CO2 gas systems are costly to build and complex to refuel. So there's another reason other than shifting away from the Cold War. By the time you get to the 1970s, it's that pressurized water reactors, and this is around the time period where most of them were designed, even though a lot of them weren't built until later, but especially in France, pressurized water reactors would offer economies of scale and standardized safety systems. So, which is why France eventually shifted to their all PWR strategy.
To worry about that yet in this point of the video. The reactor was placed inside a steel vessel, then inside a concrete structure. The reactor was placed
2 layers of containment. That's good.
Steam generation section, creating.
That's a key point, having these layers of containment, because Chernobyl didn't have a true containment structure. It's one of the reasons why their accident was so terrible.
A compact structure. The type of reactor was very similar to the Magnox over here in the UK.
Yeah.
It also had the ability to produce weapons-grade uranium. So that's my explanation of the reactors. Don't forget I am just a disembodied voice on the Berners-Lee sphere. Anywho.
All in all, not a bad explanation. That was pretty good, high level.
Work on the St. Laurent site began in 1963, with reactor A1 going online on the 24th of March 1969, with A2 construction beginning in 1966 and being completed in 1971. The site was operated by EDF, and as a side note, they supply my electricity here in South London as well. Right, so that's about a rough explanation of the reactors. Let's go on to our first meltdown at St. Laurent, 1969. It is the 17th of October 1969. And St. Laurent A1 had been online for just a few months. Post its 24th of March 1969 startup and part of its regulation and optimization period, the reactor was subjected to different experiments and tests. As such, fuel channel loadings were different from normal operation configurations. The tests were done via hot test channels, basically an unfuel loaded channel through the reactor core. This could allow for experimental fuel and control rods to be tested without having to shut the reactor down. The hot test and fuel channels were serviced by the big old main handling device. However, it had proven to be rather unreliable, logging hundreds of issues over just a few months between the opening and October. The handling device's control system worked off punch cards. However, it would be found that there had...
I mean, this was the 60s, so yep. Very early day INC, or instrumentation and control setup.
Been an address error during the reprinting of a card sometime between the 8th and 16th of October.
Okay. I think I know where this is going.
The hot test channel was being used to test the loading of defueled fuel graphite logs. The error-laden punch card was loaded and the main handling device went into action, loading the graphite logs. However, it was not loaded into the hot test chamber. Instead, an active fuel-containing channel received the graphite log. Operators didn't notice the error, and in an effort to save time, didn't do a flow test on the hot channel, which also might have highlighted the error. Almost as soon as the loading of the fuel channel with the extra material was complete, the temperature in the channel started soaring. What was happening was that the addition of graphite had caused a reduced flow of coolant gas to the channel.
Yeah, and this is a perfect example of very early days of automation and the risks associated with that. Data mismatch, your classic human-computer interface failure. And this mirrors, so in modern INC instrumentation controls concerns, you need to have your software validated. There is a strict software quality assurance program, like in almost an independent unit within the own site, depending on how your organization is set up. But the point is, software validation, peer checking, independent verification of the software is mandatory before you even have it operate anything in the plant. And incidents like this is what caused this nuclear safety culture evolution.
In a matter of seconds, the fuel's aluminium-zirconium alloy cladding began to melt. At 7:05 in the morning, the fuel, some nearly 50 kilograms of uranium, had melted. The reactor was shut down, and it would be out of action for quite a while.
Yes, so localized overheating and cladding failure. This 50 kilogram of molten uranium was confined within this channel. And this would be considered a partial core damage or a partial meltdown. And graphite does have low thermal conductivity, and CO2 has limited heat capacity. So this is a downside of both of those, because water has great thermal conductivity and great specific heat. So these thermal hotspots are a lot faster in this type of reactor design. You mentioned in a matter of seconds, and it would take a while if you had a channel type water reactor to compare. Interestingly enough, Chernobyl, in the case of that, was actually, since it was actually water cooled, and it was technically a boiling water reactor, a really janky one with that was graphite moderated. But there's a reason why but if this sort of thing would even happen there, it would have been slower, which is interesting. Not saying Chernobyl's was a good design, but this just points out the vulnerability of a gas-cooled, graphite-moderated reactor for this specific scenario.
Fuel that melted was luckily fairly newly inserted, meaning it wasn't heavily irradiated, but it would still be a big mess to clean up. Cleanup was done via remote-controlled equipment. However, extra work via human intervention had to be also employed. Workers' exposure time was limited to just
remote
10
operation was pretty primitive back then.
minutes per session.
So this is precursor to modern ALARA practices. Short exposure time and remote tooling were typical even back then. And today, radiation dose limits are carefully monitored using TLDs, that's thermoluminescent dosimeters, so people track the dose real time to ensure really tight exposure management and good radiation protection practices.
It finally went back online nearly a year to the day on the 16th of October 1970, costing France's nuclear industry millions of francs. The incident was played down to the French public with officials.
I mean, compared to some of these others you hear about, it wasn't necessarily that significant. I mean, something like that would be reported like crazy today and require all kinds of regulator intervention, probably end up taking the keys away from the operator, so to speak, until they overhaul safety systems, safety procedures, and safety culture. But yeah, back then that's consistent with the way things were.
Instead playing up the quick and efficient cleanup and restarting of A1.
Yeah.
But another melting for spicy material would blight the big power plant just over a decade later. 1980. It is the 13th of March 1980, and on the face of the newer of the two gas-cooled reactors at St. Laurent, named A2, everything seemed to be running as normal. At around 5 p.m, loading was underway of two of the reactor core's channels. Reactivity around the reactor vessel unexpectedly and dramatically rose. Just over 10 minutes later, the cladding rupture detection system triggered a shutdown. The control rods were dropped into the core, stopping the reactor. Operators were unsure of what the issue was, but due to the reactivity in the core, the first inspections could only be undertaken on the next day. During this check, the reactor had to be depressurized. A significant amount of uranium was thus then assumed to have melted. Further analysis of the reactor would take place the following week. It was found that around 20 kilograms of uranium had melted.
It takes time to cool down and depressurize.
And fallen to the bottom of one of the fuel channels.
As well as activity levels to be low enough to do whatever level of inspection they need.
27th of March, an inspection discovered that a metal sheet from a monitoring device had broken loose due to corrosion.
Oh, all right, so this is an FME event, or foreign material exclusion event.
Had then blocked cooling to 6 channels in the reactor core. The meltdown would affect the reactor much more than what happened at A1, where the reactor would be shut down for over 3 years. The repair and cleanup works.
So in this case, it was for material intrusion, but less so of the classic someone dropped something in to the reactor or whatever exposed area, and more of a mechanical failure induced by corrosion leading to blockage. And that's just it. These CO2 gas reactors depend heavily on unobstructed flow through thousands of these narrow channels. Even a single obstruction can upset your thermal hydraulics. And there are entire programs nowadays specifically on corrosion management in reactor systems, both in terms of material selection and inspections for how you manage these sorts of things and replace them when necessary. This is something that is periodically looked at during outages.
And in June 1980, again making use of remote-controlled equipment, and like before, requiring human intervention, involving nearly 2 years of radioactive dust collection and disposal. It was estimated that during the cleanup, 29.6 terabecquerels of rare gases and 0.37 terabecquerels of iodine were released into the environment.
All right, so to give you a sense of scale, terabecquerel, yeah, that sounds like a big unit because a tera is a trillion of something, but a becquerel is a really small unit. To give you a sense, Chernobyl released 1.8 million, more than that, of iodine-131. And iodine-131 is the isotope of concern for a sudden puff release. It doesn't have a long half-life compared to things like cesium-137 or strontium-90, but it is more radioactive in the short term for early release. Entire risk models at nuclear power plants are modeled around this specific isotope. And there's even a number for dose equivalent, iodine-131, that gives an equivalent based on an aggregated puff release that you would get in these accidents. Granted, you don't want to release anything. And in the case of, he said rare gases, so noble gas, such as krypton and xenon, are indeed fission products. However, they're less harmful to humans because iodine-131 gets uptaken by the thyroids and it increases your risk of thyroid cancer. But krypton and xenon, you're just going to inhale and exhale it. It's a noble gas. It's non-reactive chemically. So it'll give you dose, even internal dose, the short period of time that it's in you, but it's not going to stay in you for very long, which is why it's significantly less hazardous than iodine-131. So ultimately, compared to these other accidents, the radiological consequence was minor and localized.
This time, however, it wasn't really operator error, but a sign of the general poor management of the site. Reportedly, warnings were ignored that corrosion was present in the reactor vessel, most notably from an inspection in January 1980. Again, the event was played down, and after the cleanup of A2, the reactor was pressed back into service. But the lifetime of domestically produced gas-cooled reactors of France was nearing the end. The UNGG reactors across the country would be shut down in the following decade, in favour for light water designs. This was rather the case at St. Laurent, with A1 and A2 being shut down.
Light water meaning just regular water as opposed to heavy water that uses deuterium instead of regular hydrogen.
Early 90s in favour for the much newer and more modern B1 and B2, which still operate on site to this day. But even though shut down, St. Laurent's gas-cooled reactors,
those are pressurized water reactors,
caused a media stir when a documentary was released in 2015, The Aftermath. So this 2015 documentary, named Nuclear: The Politics of Lying, would posit that after the 1980 meltdown, EDF had released reactive material into the Loire River for 5 years after the accident. In response to the documentary, the then at the time of the release, head of EDF, Marcel Baiteau, gave a rather humorous statement regarding the incident. "It's still not much, it's not good, but it doesn't matter. If this was done, it was with the approval of the public authorities. We could not have done otherwise."
So this 5 years, this claim was indeed unverified and later dismissed by the French version of the Nuclear Regulatory Commission. And one other thing about plutonium traces, since again this is a uranium fueled reactor, plutonium does show up at the end of core life, and measuring plutonium traces in sediments doesn't imply dumping. It could even be evident of microscopic particulate release during decommissioning, because after all, the numbers were well below public dose limits, that is to say in the microsieverts per year range.
Samples along the river found traces of plutonium, which could only have come from the St. Laurent nuclear reactors.
But again, it could be decommissioning.
But the levels were below a discernible health concern. An investigation and subsequent complaint without further action was filed against EDF in 2016. Both major incidents at St. Laurent would go in the 1990s on the INES scale at a level of 4, which puts it on the same rating as incidents such as the Tokimura incident, which I've also done on a video, which will be linked around here. So that's my video on the St. Laurent reactor meltdowns. Hopefully I haven't angered EDF too much to shut off my electricity. So it's scale time. It's going to only really be a 1 or maybe a 2. And this is what I've got for my root cause analysis card. Do you agree?
Wow.
Let me know in the comments below. This is a Plain Default production.
I like his root cause analysis card. Let's go back a bit. All right, so we got warnings ignored, sure. Bodged safety, or botched safety, I guess. Time pressure, yeah, to bring it back online. Legacy infrastructure, cost cutting, warning signs ignored. Recently inspected, I like that that's on there. Overly confident official and a complex system. Yeah, I could see a lot of those. And yeah, those gas-cooled ones are more complex. But ultimately, in addition to the instrumentation and software quality assurance and corrosion control programs talked about earlier, one thing is that even with these partial meltdowns, the containment buildings worked, which proved the resilience under partial failures that, yeah, the containment buildings did indeed work. Though the French officials downplaying the event did damage long-term trust, and it's best, because especially today, people are going to find out anyway. You might as well just speak it. You need to come forward about it when it happened, but there's a way to speak about it in context, lest you avoid the media failure that was the 3 Mile Island accident. And the eventual switch to PWRs did simplify maintenance and improve safety overall. The big strength of EDF is they have a standardized fleet model, both in terms of core design and maintenance, but also sharing lessons learned. Thanks so much for the recommendation, and thank you so much for watching. I'll see you next time.